Just recording this video just if any of you are curious as to just, uh, derivation of maximum range, maximum height, and the time that a projectile is airborne. So obviously we're dealing with projectile motion. And in this case, so this specific scenario that it's applicable to is when an object is projected and lands at the same plane. Like, for example, let's say this is the ground, so it's projected from the ground and it lands back on the ground. So the vertical displacement is 0. This is the only case, because other cases, then it doesn't really work. So I just want to make that clear. Okay, so first, to determine the range of a projectile in terms of u and theta, we need to find out the time, when at impact. So S of y equals uyt plus half gt squared. In this case, like we mentioned, S of y, so the vertical displacement is 0. We can factor out t from both terms. Plus half gt. Then using null factor theorem, because there's a product of two variables and it equals 0, then one of them needs to equal 0. It's one or the other. This can't equal 0. So therefore, uy minus 4.9t equals 0. The reason why it's 4.9 is because g is negative 9.8, and a half of negative 9.8 is negative 4.9. So it becomes uy equals 4.9t, so we're adding it to the other side. uy divided by 4.9 equals 2, right? So now we've rearranged for t, so that's the amount of time that the projectile is in the air. Now, the thing is, u of y is not in terms of u and theta, but we can make it in terms of u and theta, right? If we make a right angle triangle here, this represents the initial vertical velocity. It's the opposite side to the angle, theta, and u is the hypotenuse, so we can use sine as the trig ratio, since sine is opposite over hypotenuse. In this case, opposite is uy, hypotenuse is u. You multiply both sides by u, so uy is u sine theta. Therefore, t equals u sine theta over 4.9. So this is the time in air. Right? Yeah. Okay. We can use this to find the range. S of x, so range is horizontal displacement. They're interchangeable. It equals uxt. This is on your formula sheet. So for, physics QCAA, right? This is on the formula sheet. So you can sub in u of x. So in this case, it's the same thing, right? We're using a trig ratio, a appropriate trig ratio. In this case, it's cos theta because we're dealing with adjacent over hypotenuse. Adjacent is u of x, right? And hypotenuse is again u. So rearranging, you get u cos theta. So this becomes so the horizontal displacement equals u cosine theta, and then we sub in t because we want the horizontal displacement at the impact, and at the impact time equals this. So we sub in u sine theta divided by 4.9. So we get Sx equals u squared sine theta cosine theta over 4.9. Now something to note, you can actually simplify this. Now obviously, it's perfectly fine to just keep it as this, right? Perfectly fine. because now we have a range. We have the range in terms of u and theta, so we can instantly plug it in to this formula to find out the range of the projectile. Oh yeah, just to let you know, so while I write down a double angle identity that we can use, just to let you know, the reason why I'm making a video on this is because when I was going through the 2020 past paper for QCAA physics, there was a question where it was comparing two different objects, and it was a multiple choice question, so it's 1 mark, but it was a decent amount of work for multiple choice, right? You had to differentiate which option was correct. So there was obviously 4 options because it's multiple choice, A, B, C, D, and it was like, oh, object A has, it's in the air for a longer time, or it travels further, or it reaches a higher, greater vertical height, etc. Right? So I just want to show a derivation. Maybe this will come in handy on Monday. Likelihood of that, pretty low. Okay, so we're trying to rearrange for this. So what we do is we divide by 2. Yeah, there we go. And then we sub that in. So s of x equals u squared sine 2 theta over 2 all over 4.9. So therefore, s of x equals u squared sine of 2 theta over 9.8, because it goes, the denominator goes of this fraction actually goes to this, the denominator of the entire term, and then they just multiply together, giving 9.8. Range of projectile, right? Or horizontal displacement, again, interchangeable. Okay, but that's not it. That's not everything. Before I start the derivation of the maximum height, let's think about the trajectory. In the case that I specified, we know that we launch it from the ground, and then it also lands on the ground. So s of y is 0, right? But for maximum height, we want it to be here, right? And s of y is not 0 here. Now, there's a variety of different ways you can approach this, right? There's a variety of different ways, and I'm not stopping you from determining those different ways. I'm just showing one way. Okay. For this scenario, we can see that at the halfway point, so approximately where we think it's going to achieve its maximum height, we can see the trajectory of the projectile has a line of symmetry, at that point, right? So it's reflected, and if I fold this page, the lines should overlap. These lines should overlap with these lines. That's important because it is technically, symmetrical because it's a quadratic, right? That's its axis of symmetry. So we know that s of y is represented like this. In this case, t would be the variable. And guess what? V squared means it's a quadratic. Okay, so maximum height occurs here, right? But how do we get that? Okay, s of y equals uyt plus half gt squared. In this case, s of y does not equal 0. We're trying to determine s of y. Okay. Something to note. Like we said before, it's symmetrical, which means that at this point, if this is t, this is half of t. So we can sub in half of t, and we've already rearranged for t up here, so we can use that. So therefore, sub t equals u sine theta, but halved. So instead of 4.9 in the denominator, it's 9.8, right? So s of y, again, uy is u sine theta, and then we sub in u sine theta over 9.8. Again, half of g is negative 4.9, and then we sub in t. So u sine theta over 9.8, and we square it. These u sine theta times u sine theta is just u sine theta all squared, and then that's divided by 9.8 minus 4.9. And then the top, again, is also similarly to before, just u sine theta all squared. 9.8 squared is 9.9 times 9.9. These can simplify. 4.9 is half of 9.8, so then it becomes just 1 over 2, right? So then I can write it at the back, actually, because there's not much space here. These are the same, so we can factor it out. So I'm factoring out u sine theta all squared over 9.8, and then that leaves 1 because it's the same term, right? Right? So what happens here? Again, this is factored out, so it just leaves a half. So then this becomes a half times u sine theta all squared over 9.8. So then, therefore, sy max equals u sine theta all squared over 2 times 9.8 is 19.6. Okay. Max height. Okay. Let's see if this concurs with another variation. So I think v squared equals u squared plus 2gsy might also work. Let's see if it works. We know so this is another, variation. So this is also on the formula sheet for the physics QCAA external exam thing, and just on the formula sheet, yeah. At max height, brackets sy max, that's the notation I used above. Vy equals 0, right? It's not going up anymore. It stopped. So now it's going to go back down. So now it's going to actually start decelerating due to the acceleration due to gravity. So then if we sub that back in, it's 0 equals uy squared, which is u sine theta all squared. This is a very easy way to derive it, actually. So you could use this instead if you don't have this. Yeah. Okay. You get the same result. 2 times g is 2 times negative 9.8, which is negative 19.6 sy. In this case, it's sy max, so we'll demonstrate that by writing the subscript. Okay. What happens now? Okay, I subtract this, so it becomes negative u sine theta all squared, and then now I have to remove the coefficient, so negative 19.6, by dividing it on both sides. Therefore, s of y max equals u sine theta squared over 19.6. Okay, you can see these are equivalent. So through 2 different methods, they're probably not different methods. This formula was probably derived somehow through this, or a combination of, other formulas. But anyhow, we do get the same equation to determine maximum height. This one's much quicker, right? We don't need to determine the time. So yeah, obviously it's a case by case kind of thing. You know, if especially in the exam, you don't want to use a formula that might put you at a disadvantage in terms of time management. You want to use the formula where you have the specific variables. So one way to do that is write which variables you have. So that, you know. So, you know, actually define them and then write down the values that you're given in the question and then see what equations you could use or a combination of equations you could definitely employ to do the question. Anyways, hope this is useful somehow. Don't know where you'd use it. But yeah, it's definitely something interesting to think about. Yeah. All right.